We go.
Yep.
All right. Well, we're very happy to have Vazha Loladze from coming to us from Oxford. Vazha was a student of my good friend and colleague Takamichi Okui. Before that, he was in University of Tbilisi, right, as an undergraduate.
Yes.
And yeah, he's here to tell us about dynamics of the Fermion-Rotor system.
Thank you, and thank you for the invitation. Today, I will talk about dynamics of the Fermion-Rotor system. So my talk will be mostly based on two papers, one done in collaboration with Takeo Gui about a year and a half ago, and second done about few months ago in collaboration with Takeo Gui and David Dong. I will roughly divide my talk into three parts. First, I will tell you about semitone or unitarity puzzle in monopole fermion scattering. That is motivation of all of this work. Then I will tell you about the Fermion-Rotor system. That is basically effective description of this scattering process. And I will explain how in this effective description puzzle can be resolved. And after this everything, I will make connection to the another resolution of the puzzle that was introduced in the framework of boundary conformal field theory. Basically, we will show that in Fourier, Fermion-Rotor system flows to boundary conformal field theory, and it provides its UV completion. But before going there, why do I care about these problems? I care about these problems because fermion monopole system is surprisingly interesting. First, very interesting fact can be seen even in the framework of classical electromagnetism. If you have magnetic charge, that means you have particles that has magnetic field described by Coulomb law, and you have electric charge, you can go ahead and calculate angular momenta conserving an electromagnetic field, and you surprisingly will find that it is just electric charge times magnetic charge and does not depend separation between them. That means does not matter how far away they are, you always have this contribution. As a result, there is one very trivial consequence that you should generalize your angular momenta to include this contribution. And there is much more interesting consequence as well, that if you will write multi-particle states in this theory, they are not the direct product of one particle states. That follows from the fact that representation theory for the Poincare group heavily depends on your definition of angular momenta. This fact has been studied in this paper by John and his collaborators, and I think provides first very interesting and exciting physics in this kind of systems. Second, very exciting phenomena happens when you ask trivial question. Let's say this electric charge is carried by the fermion, and you ask the question, what happens if you scatter this fermion on the magnetic monopole? To be more concrete, I will have following idea in mind. Let's say this monopole is GATT monopole, and I'm scattering on its standard model fermion. And this standard model fermion has the energy that is much bigger than electroweak scale, such that I can ignore mass of this fermion, but it is much smaller than GATT scale, such that I can ignore size of the monopole. Technically, I should also assume that this fermion has small enough energy that it cannot excite the ionic excitations of the monopole. Now we will study scattering process, and it is convenient to use partial wave decomposition. However, we should do partial wave decomposition using the angular momenta we defined just now. What that results in is that instead of usual spherical harmonics, you are using something called monopole harmonics. But that's it. Now, if you do this decomposition of the Lagrangian of the fermion in the background of magnetic monopole, you will find following. That modes which has angular momenta that is bigger than minimal allowed angular momenta will develop centrifugal barriers, and they will be reflected much before they will reach monopole core. Now, I will assume that these modes will not contribute non-trivially in the scattering process. As a result, I will just study scattering of lowest angular momentum modes on the monopole. And just for simplicity, I will assume that this is minimal GATT monopole. and minimal angular momentum is 0. So we just have S waves. If I do that, I can go ahead and write down the Lagrangian, and Lagrangian will have following form. I have usual time derivative. That is just Lagrangian for radial modes. I have usual time derivative, and in front of space derivative, I have sign that is determined by the sign of E times G. That means if E times G is bigger than 0, then corresponding field has just ingoing waves. And if E times G is less than 0, corresponding field has just outgoing waves. This corresponds to this results in very interesting dynamics during the scattering. But to see this dynamics, let's be a little bit more concrete. I will consider SO5 gut that breaks down to standard model. We know that under this breaking, certain SO2 subgroup of SO5 breaks down to U1, and during this breaking, we have magnetic monopoles that we usually call GATT monopoles, and I will study scattering of standard model fermions on this GATT monopole. Additionally, we know that under this SO2, standard model fermions forms following four doublets, such that lower component of this doublet has negative U1M charge, while upper component of this doublet has positive U1M charge. Now, additionally, if we assume that, let's say, magnetic monopole has negative magnetic charge, that means that following the last slide, lower components contain purely ingoing fields, and upper components contain purely outgoing fields. Now, it's also very convenient to notice that this system has following symmetry. First of all, we have U1M, and second of all, we can exchange these doublets. That means we have additional SO4. This symmetry determines a lot about the scattering process. For example, if I ask the following question, let's take two doublets, lower components of two doublets, and scatter on the magnetic monopole. Then I can go ahead and write down conservation of U1M plus katan of SO4, and this will determine uniquely final state. And this final state will be E bar plus D3 bar. This is one of the well-known Galan-Rubakov processes, and this is underlying mechanism of proton decay. That is exactly why this scattering process and understanding of this is super interesting and important, because it is mechanism behind monopole catalysis of proton decay, and monopole catalysis of proton decay sets strongest bounds on monopole abundance in our universe. To see this, we can look at bounds coming from Super-Kamiokande. You see this red bound that is result of Super-Kamiokande search, and it uses monopole catalysis of proton decay. Basically, idea is that if you have monopole, it will be captured by the solar gravitational field, and it will start catalysis of protons and neutrons in the sun that will cause production of some mesons that will decay to neutrinos, and then you can detect neutrinos on the Earth. What you see from here is that, first of all, it is strongest. Second of all, every bound that does not depend on the catalysis are here up. So it is much stronger than anything else. Basically, everything we know about the monopole phenomenology, at least most of it, we know because of the scattering process. So it is really important to understand details of the scattering. However, the problem is that there is a puzzle. If I recycle exactly the same logic, but now I ask following question. Let me just scatter one fermion. Let's take just positron and scatter on magnetic monopole. I can go and write down exactly same conservation laws, and what I will get is that final state carries the quantum numbers that corresponds to fractional particles. Of course, we don't have any fractional particle in standard model. So What that really means is that we cannot write down consistent final state that conserves all of the quantum numbers. That is known as a unitarity puzzle and will be main subject of my talk. Basically, first I will try to resolve this puzzle, but to resolve this puzzle, SU5 GAT is too complicated. Let's go and write down effective description of this scattering process. This effective description was introduced by Joe Polchinski more than 40 years ago. What he did is following. As I told you, if E times G is bigger than 0, it corresponding field have just ingoing wave, and if E times G is less than 0, corresponding fields has just outgoing waves. Plus, we are just working for S waves, so theory is effectively 1 plus 1 dimensional. So instead of working in spherical coordinates, we can go ahead and work on infinite line, where monopole sits at the origin, such that ingoing fields are mapped to the negative direction of the axis and outgoing fields are mapped to positive direction of the axis. So we will introduce one fermion field that is purely right mover for each doublet, such that if this field is evaluated at negative direction, it corresponds to lower component of the doublet, and if it is evaluated at the positive direction, it corresponds to upper component of the same doublet. And now we can write down effective theory for this field. Additionally, I will little bit generalize the thing, and instead of a fourth field, we can have n fields. Now let's write down the theory that conserves the symmetries we know that is conserved during the fermion monopole scattering. So first of this symmetry is exchange symmetry of doublet. This is actually easy part. We can write down Lagrangian that conserves exchange symmetry of these fermion fields. Harder one is following. As I told you, this fermion field was constructed such a way that one side it is one lower component, other side it is upper component. But upper and lower component has different U1M charge. That means when we act on psi with U1M transformation, transformation law has following form, which contains this f function that is basically step function that changes the sign. Now we should write down the Lagrangian that contains that conserves this symmetry. Of course, it is impossible to write down such a Lagrangian that contains just a psi field. Because of that, Polchinski have introduced extra degree of freedom. As this extra degree of freedom is just quantum mechanical rotor that couples with fermion field, just like gauge boson would couple, but its spatial dependence is fixed by the derivative of this step function, and it is basically a regularized delta function. So it couples to fermion only very close to magnetic monopole. Now, additionally, rotor have got U1M transformation, and after that, you can check that this Lagrangian is explicitly invariant classically under U1M. Then you can check that it is explicitly invariant under SUN, and after that, you can check that the symmetries are anomaly free. Only non-trivial anomaly is anomaly for U1 square anomaly, and it is also 0 because it is proportional to integral of fx times derivative of fx, and because this function is antisymmetric, derivative vanishes. Additionally, we also introduce a kinetic term for the rotor, but meaning of kinetic term will be clear in a minute. Before that, as we said, we introduce the rotor to guarantee conservation of U1M charge, but introducing of rotor makes another symmetry anomalous. And this symmetry is symmetry of fermion number. If you write down conservation of fermion caret, you will see that non-conservation is proportional to derivative of rotor field. Now you can go and solve equation of this equation, and you will get that changing number of fermions before and after scattering is proportional to change of value of rotor before and after scattering. So there is instanton-like configurations in this theory that corresponds to non-zero delta alpha. As you see, this system is, sorry, yes?
Sorry, just maybe first one elementary question. So is alpha valued on the real line or the circle or what?
Is alpha valued real line? It should be compact.
Okay, so it's like it lives on a circle.
Yeah, it is compact. Yes,
Okay.
it is
And
compact scalar. Yeah.
okay. And my other question is that you wrote this rotor just for the S wave theory, or does this rotor make sense in the full quantum theory before I do any S wave projection?
It should make sense in full quantum theory because, as I will tell you in a minute, it corresponds to ionic excitations. However, for now, I just wrote it just for S waves, just because I'm considering just S wave calculation.
Okay. And so there's a systematic kind of dimensional reduction type derivation of this
Not
concept?
very not very systematic, but there is ways to see why it should be there. But it is not, I mean, I don't think you can, I have never started from SU5 gut and get this Lagrangian, let's say. It is more like effective Lagrangian that describes what should be happening.
Okay, thanks.
Yeah. Okay, so as we said, it is like a very simple model. It is just quantum mechanical rotor coupled to the fermion, but it's very rich. Like it even have a instantons. Now let's understand. Like here, I introduce rotor as a to just conserve the symmetry because this way it is easier to make the contact with boundary conformal field theory. However, there is much deeper physical meaning under the rotor. So to see this physical meaning, it's enough to just write down charge operator for U1M. If you write down charge operator, you will see that it has two pieces. First is a piece coming from fermion current that you would expect, and second piece coming from rotor. What that means is that rotor can hold U1M charge. Let's call U1M charge electric charge after now. So that means rotor can hold electric charge, and what excitation of the rotor corresponds to is ionic excitations of monopole. So if you put unit charge on the um, rotor, you will see that its energy scales as 1 over I. But as I told you, a puzzle arising in monopole monopole fermion scattering in the situation when fermion does not have enough energy to excite the ionic state. Because of that, to replicate this situation, I will put rest of the talk 1 over I to be much larger than fermion energy. So basically, any ionic excitations associated to rotor on-shell ionic excitation will decouple. However, notice that decoupled or not, fact that rotor is written in the Lagrangian guarantees conservation of U1M charge. Because of this, in low energy dynamics, rotor will play very important role to make scattering consistent and conserve U1M charge, even though corresponding ionic excitations are not there. So, but before going there, let's first see that we have a puzzle. To see that we have a puzzle, let's look at how fermion field transforms under the symmetries. We have, as we said, SUN cross U1, and ingoing direction under this symmetry transforms at n-1, fundamental -1, while outgoing direction of the fermion field transforms as n plus 1. Yes?
Can I ask a question? Sorry, maybe I'm jumping ahead a little bit, but just intuitively from what you said, I might guess that your picture is going to be that, okay, this excitation is a heavy excitation, but that is it allows these it is the thing that actually mediates the transitions that do occur. So instead of these semyon type things, I might get completely different. This might be my picture, right? That I get completely different kinds of initial and final states, but they're sort of the scattering is more suppressed than you might think because it has to go through this heavy excitation. Is that the kind of picture you're going to end up with, or if not, I'll just let
No,
you go on. That's not the
no,
picture.
no. I can decouple the ion tower completely. I can take it to infinity. Scattering still will be consistent. So
So
picture that,
even though the excited states of this alpha you're saying are heavy,
yes,
they're still going to play a role in low energy physics. That's what you're going to explain.
not excitations, degree of freedom will play a role. Field will play a role.
Okay, that's what I want to. Okay, that's
Yes,
what you're going to
exactly.
explain.
Not excitations. Excitations will completely decouple.
I see. Okay, all right, go
Yes.
ahead. Thanks. Go ahead.
Yes. So as we said, incoming direction fermion field transfers at n-1, outgoing direction it transfers at n+1. Now we are asking the question. We scatter on the monopole or rotor one particle excitation that carries quantum numbers n-1. What comes out? So it cannot be just something that is created just fermion field. First easy guess would be that what comes out is n+1 plus some charge is deposited on the rotor. However, you can very quickly show that that is not true. How can you show that? Is that you can write down equation of motion for the rotor, and it will have following form. It has incoming current plus friction term, including rotor. Now, if you don't have constant incoming fermionic current on the rotor, any charge or energy on the rotor will decay in the time scale 4 by I over n. But remember that we should take I to be small to gap the system, to gap the ions. That means this time scale is very small and actually we cannot deposit any charge on the rotor, at least any relevant charge. As a result, this is not the answer of the problem. Final state is not n plus some charge on the rotor. Now we have a very confusing situation because we know charge cannot be deposited as a monopole. Same time, just fermion fields cannot create final state, but same time we have super simple Hamiltonian that is Hermitian and conserves the charge. So it seems unclear how can we have any consistent scattering process. And things become little bit clear when you notice following. You can write down equation of motions for fermion field and rotor field, and you will see that they are strongly coupled to each other. Everything I told you about the symmetries until now was strictly applying for the fermion fields, but actually we have never quantized this theory. Actually, we don't have any idea what is one particle states in this theory. So hope is that when you consistently quantize this theory, actually one particle state content of this theory will not align to field content of this theory, and that will resolve this puzzle. That will be my strategy to consistently quantize this theory and see what is one particle states. Of course, when you have strongly coupled theory, it is always very hard to figure out what's going on. But here, simplification there is very big simplification. Rotor, as I told you, couples with fermion with this derivative of step function that is regularized delta function. And in the limit where monopole size is 0, it is basically delta function. That means theory can be seen following way. It has three regions. First, incoming region, where theory is just theory of free right moving fermions. Second, outgoing region, where theory is just theory of free outgoing right mover fermions. And small region in between, where you have strong coupling. This simplifies situations tremendously. Basically, what happens is that at least every correlation functions we try to write down, corresponding path integral comes out always to be Gaussian, and you can actually perform path integral. As a result, strategy would be to look at correlation functions in this theory and read physics directly from the correlation functions. First correlation function we can look at is correlation function that contains any number of insertion of fermion fields. That was calculated in the original paper by Polchinski. He showed that this correlation function has following form. There is free correlator part, which means you set rotor to be 0. You literally imagine that it is theory of free fermions and calculate free weak contractions times some multiplication factor, which is also very simple. It is just integral with frequency of two functions, where each function contains exponential insertion associated to fermions and incoming and outgoing fermions. After you can have that, you can calculate any correlation function just involving fermions. So first we can calculate is, let's say, two-point function. Let's look at two-point function. If you calculate two-point function, you will get what we was expecting. If you have two fermion insertion such that both fermions are inserted before rotor or both are inserted after rotor, you will get just free propagator for wire fermion. That corresponds to the fact that, as I told you, theory before and after rotor is just theory of free fermion. Now, if you calculate two-point function such that one fermion is inserted left to the rotor and second fermion is inserted right to the rotor, this is 0. That is also consistent to the story I told you. Because remember that this fermion carries U1M charge that flips the sign when you go on one side to another on the monopole. That means by charge conservation, this should be 0. So far everything is consistent. Now, to really make sure that what we write down is really effective theory for monopole fermion scattering.
Sorry, can I ask a question?
Yes,
Sorry, just to keep interrupting, but if you don't mind.
no problem.
Yeah, so this kind of thing is the reason that I kind of was asking before, and I kind of want to ask again. You know, once you've done this projection onto the spherical waves, there's a definite difference between the left and the right of the rotor, the monopole, yes. But in
Yes,
the three-dimensional case, obviously there's not, right?
yes,
There's not,
yes,
and so that's part of the one of the things that I don't know if it's important, but I just wanted to get your response. All of this work seems to be always living in this two-dimensional projection, right? And
yes.
so can you comment on how does this feature look in the three-dimensional picture?
Uh,
There should be local fermion fields, I would guess, but now you can't
yes.
tell which side they are in from their, you know.
I
What does
I
this even
think
mean? What does this picture even mean in the three-dimensional picture?
I mean just this picture in three-dimensional picture simply means that something is incoming and something is outcoming. So one
But you're
fermion
writing
is
it in terms of T and X, right? And this X is either on one side of the rotor or the other. So this is some unfolding of the two-dimensional, the projection, right? Where you've just somehow, instead of
uh,
having things bounce off the origin, you're making them go through the origin. But I don't know how to do that in a three-dimensional picture, right?
just imagine that X is R and psi is just a function of t minus x if it is this side, and it is function of t plus x if it is that side. So one is just incoming and second is just outcoming fermion. But I agree that it is very confusing to think in three dimension, whatever I will tell you today.
Okay.
And I don't know how really it is embodied in fully. But
Okay.
just psi field, it is incoming and outcoming.
Okay. Thanks.
Okay. But now to make sure that this effective theory really describes fermion monopole system, let's go ahead and reproduce first Gallang-Bakov processes. To do that, let's fix the n equal 4 to make contact with GATT. and look at for 2-to-2 processes where we don't have semitone puzzle. So we first make sure that they are there. So you can easily show that if you have just insertion of two fermion in incoming direction, only non-zero correlation function is given this way. Now you can translate this back to the standard model doublets. Each fermion corresponds to different doublets, and you can read from here that negative means it is a lower component, positive x means it is upper component. So this really corresponds to process u1 plus u2 goes to e bar plus d3 bar. And with this way, you can reproduce all of the Karan-Rubakov processes, at least which does not have semitone puzzle. After that, we can look at what happens with semitone puzzle. To look at what happens with semitone puzzle, we need correlation functions that will have one fermion insertion in initial direction, because simplest simplest unitarity puzzle appears when you have just one incoming fermion, and we should find some operator outcoming direction such that correlation function is zero, not zero. But if you just use local fermion fields, you can very easily convince yourself that any number of fermion insertions, just positive side of the axis, will give you always vanishing correlation function. That, of course, follows from the symmetries, and that is connected to semitone puzzle. That is exactly why we have semitone puzzle. Because we cannot easily write down final state. However, that cannot be end of the story, because as I told you, it is very simple system, and we should have something. We should have some correlation function that is non-zero. Otherwise, we could not have consistent scattering. And actually, about 1.5 years ago, we have found this operator that gives you non-zero correlation function. And this operator is not operators that consist only from the fermions, but it is non-local operator that consists from fermion as well as rotor insertion, but rotor is inserted at the right coin of the fermion. You can write down this correlation function, and you can explicitly show that calculation gives you that value of this correlation function is just free propagator for Weyl fermion, meaning that whatever is scattered on the monopole, this one particle state, 100% scattered to something that is created by this operator. Simply because you can do LSC reduction and you will get that matrix element is 1. After that, we should identify actually what is the state that is created by this strange operator. To do that, first we look at the symmetries. Let's see how this new operator transforms under SUN. We know that fermion field is fundamental and rotor is singlet. So under SUN, it is just fundamental. Under U1M, psi has charge 1, and exponential I alpha has charge -2. So it has charge -1. So final state carries charge n-1, as it should be, because your initial state was carrying n-1. We said that the system conserves the charges. This is not surprising. But what is surprising is that even though this is non-local operator, if you go ahead and calculate two-point function of this non-local operator, you will get propagator for free Weyl fermion. So final state is just free Weyl fermion carries charge n-1. But remember, we did not have corresponding fundamental fermion field in our Lagrangian. But rotor and fact that it is strongly coupled with the fermion saved us. And we have now this non-local operator that interpolates the states that can be the final state. Actually, we can go ahead and do even a little bit more. We can define these two operators. First is defined such a way that when x is negative, it is just fermion, and when x is positive, it is fermion times rotor. And second is defined opposite way. It is fermion at positive side. It is fermion times rotor at negative side with extra minus sign to account for charges. What you will see is that first operator interpolates n-1 state on whole axis, not only in incoming direction. And second interpolates n+1 state on whole axis, not only in outcoming direction. So what does that mean is that when I told you that if a times g is positive, it is just ingoing, when a times g is negative, it is just outgoing, that was statement about the fields, no, not about the one particle states in the theory. One particle states actually are there. For e times g bigger than 0, you have one particle state that goes in, as well as one particle state that comes out. And same thing for e times g less than 0. Only thing is that part of these states are interpolated by non-local Fermion-Rotor operators, not just by fermions. This obviously solves the puzzle because you have needed final state to do scattering, and actually you can show in all of the cases that actually S matrix is just unit matrix and transition happens 100% probability.
So
This, yes,
doesn't this double the number of states in the theory?
this doubles number of states in two-dimensional theory. Yes.
But not in 4D?
I don't know what happens in 4D because I don't know how it is implemented in 4D. In 2D, it's obviously doubles it because we started something and we have twice more. But it's important that it does not double field content of the third, even in 2D. In 4D, what happens about the states, I'm not sure.
So
Because
sorry,
I mean, it's very easy to make the mistake before we know how to uplift this solution in 4D.
so is it correct to say, because I'm not following as all the details, but is it correct to say when you say it's doubling the states in the 2D theory, that's because compared to before you doubled, certain states were only allowed to be incoming and certain states were now
Exactly.
only allowed. And now the doubling means that all of the incoming states, there's a corresponding outgoing state.
Yes.
So there's
Yes.
now a symmetry between incoming and outgoing. So
Yes,
at least
exactly.
at the end of the day, you might expect that to be a reasonable thing, right? I mean, it doesn't, it's
Yes.
not a crazy doubling. It's the kind of doubling that you would expect from the higher dimensional picture.
Yes, exactly. And notice that that's only way if this, not only way, but one of the logical way, if this theory has consistent scattering, something like that should be happening. Because, I mean, otherwise what you will get as a final state. Yes. Now I will move to part where we can make the connection to another resolution, but if there is questions before that about the solution, any other questions?
Can I
Okay.
just ask, I mean, it seems like if your picture is right, that there might be a relatively understandable, four-dimensional picture of this, right? Because you're saying that if you properly understand what the interpolating fields are, and in particular, you're focusing on a very qualitative feature, which is their locality, right? Just the fact that they are, independent degrees of freedom in the sense of their commutators, right? So
Yes.
I'm just wondering, have you tried to think about that? Do you feel like is that hard, or do you think it's just something that might just require more thought, or do you have any ideas?
I mean, first of all, as you asked me before, like we need to really understand how this rotor, let's say, works in 4 dimension. Does it couples to other waves or not, and things like that. Let's say other partial waves. Does it couple other partial waves?
Okay.
And I mean, after this everything, I think we can understand this. But yeah. For example, like what John asked is a very important question. Does it double the states in 4D? If it doubles, it is different thing. If it does not doubles, it is a different kind of scattering process that I don't know also. Okay, now let's make the connection to another resolution. To make contact, let me tell you once again that how this theory looked like was that we had incoming direction where it was theory of free fermion, right-moving free fermion, outgoing direction where it was theory of right-moving free fermion, and very small region in between where we had strong coupling. And the role of this strong coupling region was to conserve our non-anomalous charges. Now, it seems equivalent to ask following question. Instead of considering this right-moving fermions, let me fold system such that incoming direction becomes left-moving fermion. Outcoming direction is still right-moving fermion, but instead of this region where it was strongly coupled, I put the boundary. This boundary will correspond to monopole, and I will ask this boundary to conserve non-anomalous charges. Now I have the situation where every fermion that is ingoing to boundary carries, let's say, negative charge, and every fermion that is outgoing from the boundary carries positive charge. And obviously here is also unitarity puzzle, because you should say what happens if you saw just one fermion on the boundary. Good thing is that when you formulate this problem this way, you basically have CFT with boundary, and there has been a lot of work about the understanding conformal field theories with boundary, at least in 2D. And you can apply here machinally something called boundary conformal field theory. This has been done about 2 years ago in this paper by Van Beest, Smith, Del Mastro, Komodowski, and Tong. And they found following. If you slow just one fermion on boundary, what comes out is outgoing fermion attached on the topological line. For the purpose of my talk, it will be enough to say that what comes out is something that is created by non-local twist operator T and fermion field. On top of that, they found that scaling dimension of this seemingly non-local operator is 1/2. So what you create is just free fermion. On top of that, they also found that this thing transforms under the symmetry group as n-1 as it should be, because we need to conserve the charges. But additionally, they found mild non-locality. Yes, what does mild non-locality means? If you are working in Euclidean space-time, that is convenient if you are using conformal field theory, this line corresponds to branch cut in your theory, and if you drag your fermion operator along this branch cut, it will pick up the phase. However, rotor system was formulated in Minkowski spacetime, and it seems very hard to understand what does it mean in Euclidean spacetime. But it is possible to understand what twist means in Euclidean space, in Minkowski spacetime, and what this means is following. You have this operator, which has trivial commutation relation for incoming fermion, so it commutes. It has also trivial commutation relation for outgoing fermion if it lives outside the end of topological line. But if this fermion lives between end of the topological line, or same thing as outgoing fermion, and boundary, somewhere here, you have non-trivial exchange relation, and you will pick up the phase, extra phase here. Now, what situation we have is following. In Fermion-Rotor system, we have non-local operators that creates final state. In boundary conformal field theory framework, we have also non-local operator. This matches. Also, in Fermion-Rotor system, we have that this non-local operator transforms as n-1, BCFT transforms also as n-1. In Fermion-Rotor system, we have that this seemingly non-local operator has free two-point function for Weyl fermion. In boundary conformal field theory approach, you will find that scaling dimension of non-local operator is 1/2. Of course, this is equivalent statement. So far everything matches. Now, conjecture is following, that Fermion-Rotor system in far IR, after ionic excitation decouples, flows to boundary conformal field theory, and it provides sort of UV completion for boundary conformal field theory states. But there is one extra thing to show before we will conclude this. And this one extra thing is that, as I told you, on top of this everything, they also found this mild non-locality in exchange relations. And we have shown this in our last paper. Actually, calculation is not hard. It's actually pretty simple. What you do is that you write down equation of motion of the rotor in the limit where fermion energy is much smaller than gap of ionic gap, excitation gap, and you can find value of rotor at t minus x as a value of rotor at t plus integral from outgoing fermionic current. Now you can go ahead and calculate commutation relation between fermion and rotor. Because you are calculating same time commutation relation, with first term it commutes, and with second term it is commutator of current with commutator of psi. We know how to calculate this commutator. And when you do this calculation, you will get following expression, where what I want to highlight is this two-step function dependence. So first step function tells you that if y is negative, so if you have incoming fermion, they commute. This, of course, corresponds to the fact that twist operator commutes with fermions that are incoming. Second step function tells you if y is bigger than x, also commutator is 0. That also corresponds to the fact that if you have fermion field that is farther away from the boundaries than end of the topological line, they commute. It commutes with twist operator. Only non-trivial commutation relation happens if y is between 0 and x. And for this value, we can actually calculate exchange relation. And when we calculated exchange relation, we exactly got exchange relation previously obtained in CFT approach. Yes?
Sorry, so it's not really clear to me what is the precise relation between alpha and t. I mean, t was somehow additive, whereas this alpha in the rotor sim is multiplicative. You see what I'm saying? So what I don't really understand.
This was just notation. When you are creating states, you are acting first with t and then fermion field on the vacuum. It's
So what is can you write a simple formula for the relation between t and alpha and these, what's the map?
I will write on next slide.
Okay, thank
Yes.
you.
Yes.
But this is some sort of an operator statement
it's some sort of
about inserting the t's or the alphas together with the fermion fields that you're mapping between the two pictures.
Yes. There is exact relation between these operators.
Okay.
Okay, so we got this. Now, I will tell you in advance. So what relation would be is that actually exponential I alpha is t. And that is shown by these exchange relations. And I think it is already enough to see that because it has same exchange relation, it should be same operator. However, we can do much more. What we can do is that we can bosonize this system. You can bosonize such a way. You have incoming direction, you will introduce one boson for this, and you have outgoing dimension, another boson for this. Then you can go ahead and solve equation of motion for alpha, and you will get for alpha expression in terms of these bosonic fields. And that is exactly the expression previously found with CFT techniques for T. So we can now conclude that T is exactly exponential I alpha in this picture. So let me say what happens, what really happened. What really happened is that we introduced rotor to account dionic excitations of the monopole and same time guarantee conservation of U1m charge. But when we are talking about the theory at very low energy, ionic excitations decouple, but the fact that alpha was in the Lagrangian was guaranteeing conservation of U1m charge, and this forces alpha to play the role of twist operator in low energy theory and make possible to have consistent scattering processes. Another way of saying is that Fermion-Rotor system actually provides UV completion for these states in boundary conformal field theory. I can give you more evidence. So what we also have done is that we have generalized this system. Before I had n fermion coupled with one rotor. Now I can have n fermion coupled with r rotor, where r is less than n. What I will get is the system that has following symmetry. I have U1r, under which rotor transforms, as well as fermion transforms non-trivially, in the sense that incoming and outgoing fermions have different sign charges. I have also leftover U1 n minus r symmetry, under which rotor does not transform, and fermion transforms trivially, such that they have same charges. Now, additionally, if I satisfy following relation for charges, all of mixed anomalies will cancel, and this will be anomaly-free symmetry group of this theory. Now, that is a theory that was previously, yes?
I don't think there was a
Oh,
question.
okay.
Sorry, I don't think there was a question. Go ahead.
Yeah, okay. So we have this anomaly-free symmetry group, and in CFT literature, such a system have been studied before with such a symmetry. And in all of these cases, we showed that in IR, this system flows to corresponding boundary conformal field theory, conserving U1R cross U1 n minus r on the boundary. In all of these cases, we found set of twist operators that are always written in terms of exponential I alpha. But now notice that we have multiple operators, so it carries additional index. These twist operators, first of all, have exactly same exchange relations that was previously found using CFT techniques. And second of all, we can do also this bosonization trick, and we can explicitly found the form of these operators, and it will agree the form of twist operator obtained with CFT techniques. What seems to be happening is that rotor and its generalization provides UV completion for boundary, or sometimes called Carty states, in chiral theories with boundaries, at least when boundary conserves abelian subgroup, abelian group, and at least when we are in 2D. Now, at the end of the talk, before summarizing everything, let me also give you one interesting thing that is common, similar in BCFT and rotor, and probably will convince you more than these theories really describe same IR physics. And this thing is that if we look at the SIG theories, let's say I will look at SO2 gauge theory with magnetic monopole, so it is broken to U1. But now let's say this SO2 has Witten anomaly. Let's say it has odd number of doublets. So then you can, in these cases, you can always find that in the corresponding Fermion-Rotor system, Grassmann odd operator will get vacuum expectation value. That corresponds to the fact that in the theories with Witten anomaly, usually instantons have odd number of fermion zero modes. For example, for n equal 1, you will get following operator that have vacuum expectation value. Here it is psi insertion plus rotor insertion, and rotor is inserted in such a way to kill U1m charge of psi, because we cannot break gauge charge spontaneously. In BCFT, cannot do equivalent calculation because you don't have rotor. But what you can do in BCFT is that you can compactify this system on the circle, and then you will find that this compactified circle in this compactified system has odd number of Majorana zero modes. That usually also signals the fact that this has some thickness. This system has some thickness. Not only for this does not happen only for the theories that are thick in 4D, but also for the theories in 2D that does not have any 4D completions, but you can write, let's say, BCFT and Fermion-Rotor system kind of models. You will always find that when one has a number of Majorana zero modes, second has wave for Grassmann operators. By the way, this odd number of Majorana zero modes also happens for Fermion-Rotor system of the circle. So that's last argument what I want to give you, and this actually shows. Yes.
Sorry, can you say a little more? I really didn't get the connection between the anomaly and the VEV of the fermion operator. Can you just say a little more about that? I didn't get it at all.
I
So
don't
anything
know. I don't know if there is like explicit connection. I'm simply saying that when Grassmann operators have very usually it is very hard to quantize this theory. It's somehow thick theory, right?
So you're really making some kind of
Yeah, exactly. Nothing
consistency.
concrete.
You're making
Yes.
you're making a consistency argument. You're saying suppose the theory made sense, and then
Yes.
somehow you would conclude that the theory
Yes.
has to have a VEV for a Grassmann odd, for a Grassmann
Yes.
variable, which seems crazy, which seems like that just can't happen.
Exactly.
So what is it that's causing the VEV? Is this something you can explain, or is it can you explain then what is leading you to the conclusion that there's a VEV?
Just calculation of correlation function.
You just calculate the 1-point function, and in this,
Yes.
with all this stuff, and you get this result.
Yes, you just balance the charge of psi to because you cannot have something that carries gate charge because it would be zero. But the moment you will balance gate charge, you will see that correlation function is non-zero. Just 1-point function is non-zero. But I don't know if there is.
I have another question I'll ask later, but thank you.
Yeah. Okay. Thanks. And let me summarize what we are really saying. What we are really saying is that Fermion-Rotor system provides effective description of scattering of lowest partial waves of the fermions on the monopole. In this framework, the well-known unitarity puzzle is resolved by recovering missing states that are recovered because they can be interpolated by composite Fermion-Rotor operators. So even though in IR, any physical excitation related to rotor or any dionic excitations, decouple, the rotor still plays a very important role because introducing it in the Lagrangian guarantees conservation of U1M charge, and this forces the rotor to play the very important role of twist operator in far IR, and this makes scattering consistent. This also means that in far IR, the Fermion-Rotor system flows to the boundary conformal field theory. However, of course, that is not end of the story, because as we already said, the story is purely 1 plus 1 dimension. We need to know what this really means in 3 plus 1 dimension, because our world is 3 plus 1 dimension. Other thing is that we really not need to know what happens when you include small non-zero fermion mass. And we need to show that this solution is continuous between massive and massless cases. Third, and I think very, very important question is that we know that Kalan-Rubakov processes and proton monopole catalysis of proton decay have some topological nature. So they are connected to some instantons. So we need to understand how this story I told you today is actually connected to this topological nature. I think very interesting would be to investigate connection to recently introduced abelian instances. And at the end, when we do this everything, we need to go back and evaluate monopole catalysis of nucleon decay again, because any change in this process could have huge phenomenological significance for monopole phenomenology and correspondingly for cut phenomenology. But of course, that is subject for future work. For now, thank you for your attention, and if you have any questions.
Other
Questions
questions?
from not Marcus.
Yes, from not me.
Can you hear me? Can you hear me?
Yes.
Hello? So for boson scattering, there's just no way to conserve angular momentum, so it must bounce back instead of passing through the monopole.
Sorry?
So if I have monopole and a boson, there's no way to conserve angular momentum, so it must bounce back when you throw a boson on a monopole.
Okay.
Is that
Boson.
what people believe, or?
Boson on the monopole. I don't know. I have never.
Or is there a reason why this story is limited to fermion and monopole scattering instead of, like, why does it have to be fermion?
Why does it have to be fermion? I mean, in this case, I was simply interested by proton decay. That is where from we started. That's why we studied fermion. I don't really know what happens when you have boson.
Okay.
Probably other
I
people
mean,
know.
maybe a similar kind of related thing is, it looks like this is also in the context of fermions. It looks like it's somehow, this puzzle is only there if you have chiral fermions. Is that correct? If you had a vector-like theory, would you still have these puzzles, or would you just have?
You started with vector-like
Yeah, I
theory.
mean, I could just double the, make the SU5 theory vector-like by just adding if I have a 5 bar and a 10, I'll add a 10 bar and a 5. There we go. Now it's vector-like, right?
Okay,
This was a toy theory, just asking similar question, like what's really causing would I have a puzzle then, or I would
I
just
think
have,
puzzle is caused from the fact that when you project to S waves, theory is chiral, yes.
so that, I see, yeah, so in the
Yes,
limit.
because
where
you
the
don't have
fermions
simply outgoing fermions, yes.
Okay.
Hi,
So- Go ahead.
this is Xincha. Just for the Rubical process, you have two fermions coming in and then which turn into the other two fermions, right?
Yes.
Because the correlation function is non-zero. But do you
Yes.
have the, say, two fermion coming in and the two composite fermion coming out? Is there a non-zero correlation function or not?
Depends. That's a very good question. Depends how close is these two fermions to each other. If they are far away, they will pass. Each will pass. If they are such a close away, such that you can have 2-2 scattering, they overlap at the monopole, then they will give you 2-2 scattering.
Sorry, I'm not sure I completely understand this. Because you have one fermion, you are turning into a composite fermion, right? That is in some sense. Well, it's another fermion was created by the composite operator. But I
Okay,
would say, can these two fermion turn into still the original two fermion, but created by the composite operators? Or they have to go into they have to go into two different fermions?
If Okay, so you are basically asking, I have this 4-point function, but I could have another 4-point function where I have two non-local operator insertions, right?
Right.
Yeah, that is completely correct. That is what you can have. However, notice that if these two composite operators are close to each other,
Mhm.
quantum number of these two composite operators will be same as quantum number of 1, 2.
Mhm.
And because here only thing we can measure is quantum numbers, I mean, that is it.
So
Right, we can't tell the difference between E bar, D bar, and U1, U2.
We can't
Seem-
tell the difference E bar, and
You're saying there's a process where U1, U2 scatters and comes out as U1, U2 with some twist operator.
yes.
But
And
this Kalin-Rubikov process already unitarized the S-wave scattering. So how is there any room for an additional final state?
I'm saying that this second thing is happening only if outgoing fermions are, I mean, if scattering is 1 to 1, like first you scatter one and second you scatter second with some
Well,
delay between
In an
two.
S matrix, I just have some asymptotic initial states. I don't get to say
Yeah, but
which.
you can definitely have disconnected diagrams, right? This corresponds to disconnected diagram when you have to
But in an S matrix amplitude, there's
I mean
just I specify initial states and final states. And
yes.
this process, the Rubikov-Kalin process, unitarizes the partial wave scattering. So there's no possible probability.
that was me. I think
Okay.
I'm sorry. I think I raised my hand and it did that. So I apologize. I'll try to stay still.
It would
Yes.
violate unitarity to add an additional possible final state if you
No,
already have.
it don't because second process corresponds to 2 times 1 particle scattering, not 2 particle scattering.
I mean,
I mean, you can
maybe a concrete version of this question is when on this slide here, when you're talking about this process, are you assuming that all particles are in an S wave?
Yes.
Right? And
Yes,
so
I assume all particles are in S wave.
now, if they're not, of course, you could have these guys in other partial waves, and then they could scatter. So is what you're saying is that you could have different final states in other partial waves? Is that the correct statement?
I mean, in other partial waves, it is just same particle because they are just reflected by centrifugal barrier.
Well, because John was asking, doesn't this process saturate S-wave unitarity? And so I'm
This
asking,
process saturates S wave or unitarity,
yeah,
but
so the
this is
other
I was
processes with other particles are cases where the particles are not all in the S wave. Is that correct, or?
no. Other processes
Oh.
I was talking about 2 consecutive scattering.
Okay,
Not scattering of 2 particles, but you scatter first 1 particle, detect, and then you scatter second particle.
but that could still be decomposed into a partial wave decomposition, right?
Yeah, that is still S wave. Yes. I mean, quantum number, the final state will be still 1, 2. If you look at large distance. But I don't think it's any.
In the initial state, I'm just specifying some radial momentum for particle U1 and particle U2.
Yes.
So
Okay.
in that initial state, there's no way to say what's 2 1 particle scatterings and a 2 particle scattering. It's just the initial state. And then
Okay.
it evolves to some final state.
Yes.
And the full unitarity is saturated by this process. So how can
Yes.
you add another process?
I mean, this is 2-2 scattering. Another process I was talking about is 2-1-1 scattering. It is different as matrix, right? And physically, it is just two different scattering processes.
If I'm just specifying the momenta in the initial state, how is it two different processes?
It depends how wave packets interact with monopole. Because you should specify what you are saying about the scattering. I mean, you should scatter wave packets on the monopole, right? I'm saying that if two wave packets arrive same time, then you will get this. If they arrive different time, you will get two wave packets that are attached with twist operator. If you now calculate quantum numbers of two wave packets, of course, both cases you will get same quantum numbers, simply because of symmetries. But this does not really violate any unitarity.
You're saying instead of using momentum eigenstates, radial momentum eigenstates, I'll get a different answer if I use wave packets than if I just do the normal thing of using momentum eigenstates.
Yeah, because it is different. I
I
mean,
think this is really just, look, I mean, you could say that you have, we have two scattering experiments. I do one scattering experiment, then I wait 8 billion years, and then I do
Yeah,
another
exactly.
scattering experiment.
Yeah, exactly.
Now, you could somehow say, well, that should be in the S matrix somewhere, right? Because the S matrix is all possible initial states to all possible final states. But that's somehow extremely perverse. We should just think of this as two different processes, right? We understand
Yes,
that.
yes.
And so I think that's all he's saying. I
What are
don't
the
think
two
he's
different
saying that-
processes?
Well, the two different processes, one of them is just that the particles scatter somewhere far away from the monopole, and the other one is where, the monopole just sits there. That process surely exists. The monopole is on Alpha Centauri, and then I scatter some, U1s and U2s, and they go to U1s and U2s. Of course, they're not in the S wave. That's why I was asking. So I
We're
don't know.
everything's starting in the S wave. We have a U1 and a U2. They're both in the S wave. That's my initial state.
Yeah,
Okay.
and then in that case, I think that you are forcing them all to scatter, and then that's it.
Yeah, then you are forcing them to scatter together,
Then
and
you-
then other amplitude doesn't exist. Yeah.
Right.
And that there's no amplitude that they come out as U1, U2. If I say the initial state is U1, U2.
Is that
No,
what-
if you are saying that I scatter U1, U2, there is no amplitude that U1, U2 comes out. No. Because that would break
That would
unitarity.
break-
You are completely
I think
right.
it's a
Yeah.
question of language.
But-
Yes.
It's like pretty-
Wasn't that your question?
Yeah.
You understand?
Over.
So in Polchinski's paper,
Mhm.
he used the rotor to argue that semitons were the correct answer.
Okay. We
So
can look at that way.
what
Yeah.
what is the mistake in his paper? I don't understand what he did wrong.
I think only he did everything correct, except he did not look at correct correlation function. He only looked at correlation functions that contains just fermions. He found that these correlation functions all are zero, but somehow he does not ask the questions that what is non-zero. Of course, when you have scattering, you should have some correlation function that is non-zero. When he's talking about semiton processes, he's doing classical analysis of, if I remember correctly, equation of current, and he gets that, okay, final state current carries quantum numbers that is strange. That is correct. If you take this operator I told you and calculate commutator, you will get strange quantum numbers. That is 1/2. But that does not mean anything, because if you calculate two-point function, it has correct one particle pole. It is just a one particle. It just creates one particle excitation. Anomalous quantum numbers does not really tell you anything.
So in Komargodski and Tong, they also seemed to say that the twist operator was producing this semiton.
Yes.
That's not, well, so is it a semiton or is it not a semiton?
I mean, it is one particle excitation. It is not like some strange half particle excitation. It is one particle excitation that carries a quantum number n-1. So you can, if you calculate anomalous currents, commutators with anomalous currents, you will get 1/2, but this does not have any physical meaning.
And back on slide 2 or 3, you convinced
Yes.
us there were only certain ingoing and outgoing states. Where is the mistake on that slide?
Mistake on that slide is that this is true for field content of the theory, but not for one particle states in the theory. One particle states does not align with field content because it is non-trivially quantized.
Can you go to that slide?
Yes, of course. Let's say this. So that is true for high, but it is not necessary that I actually, if you write down equation of motion for in the Fermion-Rotor model, if you write down equation of motion for psi field, you will explicitly see that you cannot write down or write it in terms of creational annihilation operators. I mean, there is no need field contents of the theory to align one particle content of the theory. So it happens all the time, right? Let's say in QCD you have pions or proton when it confines. Here also, as I told you, you have strong coupling in the system. So before quantizing the theory, asking the question, what happens, can be misleading. I don't know whether I had this, but yeah.
Can I ask a question?
Yes.
This is going to be maybe a little from, by the way, actually, why don't we do this? Sorry, if it's okay with everybody, why don't we thank the speaker, and if you're willing to stick around a little bit, maybe we can continue
of course.
discussion, but we don't have to keep everybody here who may not be as interested. So yeah, let's thank Vazha for a very stimulating talk. And we'll